this video, we want to define the curvature tensor. It's gonna be a 4 tensor, and a Riemannian manifold is flat if and only if its curvature tensor vanishes identically. And by flatness, we mean locally isometric to the Euclidean space. But before defining this, let us motivate this definition. So we want to define this curvature tensor in a way that it will help us detect flatness. We make the following observation about a consequence of flatness of the Euclidean plane. Say we have a vector z, right, at a point P on the Euclidean plane. Then we can extend it to a continuous vector field on the whole plane in the following way. First, we parallel transport this vector z along the x-axis, right? Now, on every vertical line, we're gonna parallel transport this vector. Thus we get a continuous vector field on the whole plane. Now the question is, could we have switched the order? Could we have first parallel transport this z along the vertical line, right? And then we parallel transport it along horizontal line? Or putting it in a different way? Let's say we stick with the first scenario. First, we parallel transport along the horizontal line, and then we parallel transport along each vertical line. Then the question is, along a random horizontal line here, are these vectors parallel? In other words, we want to ask if the derivative of z in the direction of x is 0. In our Riemannian manifold terminology, this means the connection of z, right, in the x direction is 0. Now for that, it suffices to check that the connection in the direction of y of this derivative, right, is 0. Well, why is that? Well, because this equation just means that this vector field is the parallel translate of this vector field at y equals to 0. Yeah, at this level, but this vector field at this level is 0. This is 0 because z in this direction was defined to be the parallel translate, right, of this vector zp along x. Right, so that means that if this is 0, then this being the parallel translate of the 0 vector field must itself be 0. So we need to check whether or not this is 0. And indeed it is. A special property of the Euclidean plane is that it has the following commutativity. And we know this is 0 because z was parallel in each of these vertical directions. So this is indeed 0. Thus our idea is as follows. We want to think of the flatness of the plane as the ability to transport each given vector z here parallel, right, in each the x and y direction interchangeably. And as we saw, that is implied by this commutativity. So maybe we could use this difference as a measure of flatness. Then under that local isometry, if these xy are the corresponding coordinate functions, then this must vanish. We can see from this that the sphere, for example, is not locally isometric to the Euclidean space, because if we extend this vector, right, first parallel transport around here, and then vertically, we see that these are not parallel transport of each other. Thus, the non-flatness, the curvedness, I guess, of the sphere is captured by the fact that this is not commutative, i.e. this expression is not 0. Now note that the commutativity of these local coordinate vector field do not imply, and it's not equivalent to commutativity of any two vector fields. If we take any two vector fields on the manifold and then write them in terms of local coordinates, then we see that this commutativity is equivalent to the following expression for all vector field xy. We call this the flatness criterion. Thus, we see that this difference should measure the failure of a manifold to be flat. So we define the Riemann curvature endomorphism as follows, right, to be equal to this. It is a 3-1 tensor, and from it we can get a 4 tensor defined as follows. And this perfectly captures flatness in the sense that Riemannian manifold is flat if and only if its Riemann curvature tensor is 0. Again, remember we say that a manifold is flat if it's locally isometric to the Euclidean space. Alright, so that's the definition of the curvature tensor. But remember, in our discussion about curvature, overview of curvature, we mentioned all of these principal curvature, Gaussian curvature, sectional curvature. So where do they come from and how do they relate to this curvature tensor? Well, to understand that, we want to introduce the notion of the shape operator and the first and second fundamental forms.